Alright, welcome to the Unit 8A video for skill number 73. I can solve problems using direct, inverse, joint, and combined variations. For this particular skill, I'll walk us through one example of each of those four variation functions. Direct first, and then inverse variation, a joint variation, and then finally combined variation. Alright, direct variation is the scenario where as the value of one variable increases, the value of the other variable increases. So if we were to graph that out and starting here, as x gets bigger, y also gets bigger. And it winds up actually being a line that passes straight through the origin like that. Perhaps y increases faster than x, or perhaps y increases slower than x. Any way you look at it, direct variation function is a variation function when graphed that passes through the origin. So the way this is set up is example 1, y varies directly as x. Y varies directly as x. So they've called out the variables for us, x and y. And then we just need to find our variation coefficient. So the k is our variation coefficient. So in step 1, we write out the variation function, which is y equals kx. And then step 2, we're going to input initial values. So they tell us y is 25 when x equals 2. So we plug in 25 for y and 2 for x. And that allows us to solve for k in step 3. And finally, we can rewrite the variation function y equals kx, but we now know k is 12.5. Typically, a problem won't ask for us just to write the variation function. It'll ask us to go a little bit further. But fortunately, this four-step process is the same for all four types of variation functions. So let's look at example 2, where I show taking it one step further. In example 2, it says the distance traveled, d, varies directly as time. So time t. So there is our variation function. D varies directly as time. When d is 12, t is 3. So in step 2, we can substitute those values in and solve for k in step 3. So finally, step 4, we're able to rewrite it d equals kt, or d equals 4 times t. And they say find the distance when time is 5. So we have the function d equals 4t. Our time value is now 5, so d equals 4 times 5. So our distance is equal to 20. On page 73b, we look at another example, but this time we're going to use inverse variation. And inverse variation says as the value of one variable increases, the value of the other decreases. So as x gets bigger, our y value is going to get smaller. As x gets smaller, our y value is going to get bigger. The left-hand side of the graph on variation functions is usually, I want to say it's ignored because we're really focusing on what's going on over here. But that's a common graph for an inverse variation function. So in the inverse variation, it says y varies inversely as x. So since our inverse variation function says y equals k divided by x, we can say y varies inversely with x. Y varies inversely with x. So our process is the same. We can plug in our initial values when y is equal to 10. Y is equal to 10 when x is 4, so we can plug in 10 for y and 4 for x. And that allows us to solve for our variation coefficient, k. 40 equals k. We multiplied both sides by 4 to get 40 equals k. And so now we have our variation function, y equals 40 over x. And in example 3, they asked us to find y when x is 5. So if we have y equals 40 over x, we can find y by saying y equals 40 over 5. And we find that y equals 8. Below this example, I've included a couple examples of what real-world problems that involve direct variation or inverse variation. So the first is direct variation. As the number of purchases go up, so does the overall price. For example, you go to the grocery store, the more food items you buy, the more you're going to pay at the cash register. The longer you walk south, the further from home you are. So if you just kept walking in a straight line in one direction, the longer you walk, the further from home you are. The next one says the larger the radius, the larger the circumference. So there's direct variation there. It's finally examples of inverse variation. Travel time goes down as speed goes up. So the faster you drive your car, the less time it will take you to get to your destination, barring any pullovers. And finally, another example of inverse variation, the work time goes down as the number of workers go up. So if one person were building a house, it would take a very long time, but if 20 people were building the house, then it could be done much faster. All right, let's look at the next two examples of variation functions. All right, joint variation is basically a direct variation function where you have two variables that are in variation. So what we have typically for a direct variation, y varies directly as x. Well, with joint variation, we're going to say y varies directly as x and z. So our example 4 gives us one scenario here where it says the volume of a box varies jointly as width and height. So our k is our variation constant, and then the two variables w and h take the place of x and z. So what this is saying is as width goes up, volume will go up. As height goes up, volume will go up. And then if both width and height go up, volume goes up. When w equals 2 and h is 1.5, the volume of the box is 12 cubic feet. So we use that to find our k value. So we write our variation function in step 1. In step 2, we substitute all the known values. And in step 3, we're able to solve for k. Now that we have k, we can solve further problems. So we rewrite the variation function v equals 4 times wh. And they say find the height of a 3-foot wide box that has a volume of 24 feet cubed. So we have 24 for the volume, 4 is our k value, 3 is our width, and we're looking for height. So 24 divided by 12 is equal to 2 feet. This should say h equals 2 feet. Finally, what we have is combined variation. And combined variation says that what we have is a combination of direct or joint variation and inverse variation. So there's a number of ways it could show up. You could say y varies directly with x and inversely with z. So that's a combined variation. You could say p varies directly with n and t and inversely with v. So there's several different ways we could write it. Example 5 actually if I remember correctly, goes into this variation function. So let's take a look at example 5. The ideal gas law states that pressure, P, varies directly with moles of gas and temperature of gas, and inversely with volume of gas. So for the scientists among us, you might notice that this is the famous Pivnert equation of the ideal gas law. If you're not familiar with that equation, you'll eventually learn it in your science class. All right, so they give us a scenario when P equals 200, N equals 0.25, and T equals 300. We can use that to solve for K, and once we have K solved, then we are able to tackle the second part of the problem. And I did that on the next page of the notes. All right, in step 1, we set up the variation function without our known value of K. So P varies directly with the number of moles and temperature, and inversely with the volume. In step 2, I plugged in the values of our known scenario, which said when P is equal to 200, N equals 0.25, and T equals 300. So we plugged in those values, and finally the volume of 3.12. Working out the multiplication, we arrive at a K value of 8.32, and we're able to plug that in for K. So now that we have a complete variation function, P varies directly with P varies directly with N and T, and inversely with V. Our variation coefficient is 8.32. They ask us to find the temperature when the volume is 0.25, the number of moles is 0.5, and the pressure is 153. So we plug in 153 for pressure, 8.32 for K, 0.5 for N, and 0.25 for volume, leaving the T variable for temperature. And if we solve that out, we find that T is approximately 9.19, and that's the solution to the problem. Now, of course, in this problem, I grossly did not use did not use units. So if you were curious, this is 9.1 degrees Kelvin. I omitted units because that's a whole nother discussion for these types of problems. But typically the units are going to be more understandable. All right, that concludes the lesson. Let's take a look at key concepts and ideas. All right, the key concepts and ideas for skill number 73 about variation functions is we should be able to set up and solve a direct variation problem. This would be the sort of y equals k times x. Usually we solve for k and then tackle the problem a second time once k is solved. Inverse variation is y equals k over x. And then we should be able to tackle joint variation, which can show up in a number of ways, but typically it'll be y equals k times x z, or maybe there's a third variable in there, xzw. Finally, there's combined variation, and combined variation is a combination of direct and inverse, and you could have y equals kx over z, and we saw that in the equation P equals, what was it, nRT over v, except I think instead of r we used k. So, all right, that concludes the lesson. Thank you.